All right, guys. Good afternoon. How are you? Been having some issues lately. It's just everything has fallen apart at the same time. So I am using a loaner laptop because my laptop, the school laptop, is at the school. And so let me know how things are. Can you guys hear me okay?
Yeah, we can hear you.
Yeah.
Okay, and I'm trying to remember was I able to get through the problem? I was trying to do biology problem last time we were together. Did I get through it, or did we have problems with the laptop?
No, we didn't get through. We had some problems.
Okay, so how about we do that first and make sure that we're okay with that. So I'm just going to do the whole problem real quick. And if you recall, it was it was on page 752B. And they told us that P of T, see this okay?
Yeah, we can see it good.
P of T was equal to 3,500 times 2 to the T over 73. And by the way, usually T is in hours, but they explicitly said that T was in minutes. And so in the problem, they gave us P, but I recommended that you don't put it in for a while. So we are trying to find the time. And what we have is we have an exponential function where we have to get that variable down from there. So the first thing we're going to want to do is don't put that big number in yet. Just leave this as P and divide both sides by 3,500. Okay, so basically we're stuck now. And the question is, how do we get them down from there? And the way we're going to get them down is we're going to undo the exponent. And the way we undo the exponent is to use the inverse, which is the logarithm. So what we're going to do is we're going to take a log base 2 to both sides. Now, if this was a 7, we would take a log base 7 to both sides. Okay? So whatever the base of this exponent is what the base of the logarithm is going to be to undo it. So I'm going to take a log base 2 to both sides. And what we have here is P over 3,500, which is equal to log base 2 of 2 to the T over 73. Now, by the way, I think I mentioned this, but I'm just going to reiterate it for, just to let you know. If you have something like this, you can simplify that by 5. If you have something like this, you cannot simplify it. Those are different problems. Okay? So basically, a good thing to keep in mind is when you have a number or something inside the logarithm, it can't be touched. So unless you have a rule or a formula or something that allows you to mess with it, you can't touch those numbers inside a logarithm. So you cannot simplify this. This would end up being what? 3 halves? Log base 10 of 3 halves. So this you cannot simplify. All right, anyhow, the reason why I'm saying that is because on the next step, I'm going to put that big number in, and we're going to simplify those numbers. So over here, though, this logarithm and the base of that exponent are going to cancel out because they're inverses, and that's how we're going to get that guy down. Okay, so over here, we still have a logarithm, and we're going to put in P now, which is a really big number. It's what, 1,792,000. So 1,792,000 divided by 3,500. Okay, so we can simplify that. And so those trailing zeros are going to cancel. And then on your calculator, does 17,920 divide by 35? $17,920. Does that divide by 35?
Yes, and it equals 512.
Okay. So now we're going to solve for t. So we're going to multiply by 73, and we multiply by 73. That's not 512. That's inside a logarithm. So the 73 goes out in front, and it's 73 times log base 2 of 512. Okay, now, if we could put this in the calculator, we would. But your calculator is a common logarithm, which is base 10. So you can't put this in the calculator. So what you're going to have to do is you're going to have to use this formula called change of base. So I'll just show you how it works, and I'll do a couple problems. So you can change this to log base 10 of 512 divided by log base 10 of 2, believe it or not. And this is called the change of base formula. I'll show you some more problems in just a second. And normally I don't show you the formal definition because it's just so easy. Why bother? But let me show you a problem. Let's say you have log base 7 of 3. You can't put that in the calculator. So you would just say, okay, well, I'll use the change of base, log base 10 of 3 divided by log base 10 of 7. You just have to remember the 3 goes on the top and the 7 goes on the bottom, and 2 logarithms are created. And now you're able to put this in the calculator. Okay. Let's say you had log base a half of 37. Same thing. You could change this to log base 10 of 37 divided by log base 10 of 1/2. And now you're able to put it in the calculator. All right, so basically what we're going to do right now is we're not going to do this all at once. What I want you to do is I want you to put log base 10 of 12 divided by log base 10 of 2 on your calculator. And we're going to make this into 2 steps. So what's log base 10 of 512 divided by log base 10 of 2?
9.
So it's exactly 9. And now we are going to take 73 times 9, which is what?
657.
Right. So the bacteria will reach 1,792,000 in 657 minutes. And we can change that to hours. I mean, 657 minutes, people aren't going to like that. You would want to say, or about 60. 60 goes into that 11 times. It's about 11 hours. So a couple new things here. First of all, remember that when you solve for a variable, you're trying to isolate it. And so that's why you saw me divide by 3,500. You didn't see me put that 1 million in right away because why bother? And then in order to get an exponent down, you're going to use the inverse. There's other ways to do it, but right now we're going to use the inverse to get them down. And so you remember the property log base b of b to the x is x, right? So you can either think of it as the property or you can think of it as the base of the logarithm undoing the base of the exponent. After you do that, you can put the 1,792,000, you can simplify inside a logarithm, you can simplify. And so we get log base 2 of 512, which we cannot put in the calculator. And so to solve for t, we're going to multiply both sides by 73, but then we have to use something called the change of base formula in order to write something we can put in the calculator. And then it just turns out that, I mean, you just work it out. All right, so I did want to finish that lesson. And now I want to know, do you guys have any questions about 15.1? Okay, well, what I want to do today then is I do want to teach 15.2 because it's just graphing logarithmic functions, and we're going to use transformations, and it should be a fairly easy lesson. And since we have time to do it, I do want to teach the lesson. So, any questions about any of these steps? Okay. So in lesson 15.2, excuse me, we're going to be graphing logarithmic functions. Okay, this is Common Core Standard F.BF.3. And what I want to do right now, I just want to graph a bunch of parents. So just like the exponential growth and decay parents all had different bases, like 2 to the x, 3 to the x, 4 to the x. The decay ones were 1/2 to the x, 3/4 to the x, 1/7 to the x. The logarithmic functions, it's the same thing's going to happen. All the bases of the parents are going to be different. So we're going to be graphing some parents. Here's the first parent. It's the common logarithm. And so remember what I said about this. This is not log of x. This is log base 10 of x. So notice that we don't have the exponential function. And we don't want to have to graph the exponential function to get the logarithmic function. We just want to straight out graph the logarithmic function. So if we want 2 points. The other day when we looked at the Explorer, we saw that the logarithms have a vertical asymptote at x equals 0, and they run up along the asymptote. And I also said that we just want to come up with 2 points, and I gave you 2 properties to find the points. So do you guys recall what x's I suggested? See, normally we pick 0, but 0 is no good in this case.
You said 1 and 0 for the first coordinate point, and then 2 and
Right.
1 for the next one.
Well, the first one, you have to evaluate it. So log base 10 of 1, log base any number except 0 of 1 is 0. So you're evaluating it, just like we evaluate the other ones. So right 1, 0 is a point. Okay, what other x? See, you can pick any x you want, but what would be a nice x to pick? The base of a logarithm, right? Because remember the property, log base b of b to the x equals x. So you want to pick a b that's the base of a logarithm. So what's the base of a logarithm?
10.
10. So we want x to be 10. So what's log base 10 of 10 to the 1? Log base 10 of 10 to the 1.
1.
Now, if this was a log base 7, you would want to pick an x that's 7. If this was log base a half, we're going to do a lot of these. So you'll get real familiar with this property. All right, so that's what you're going to graph. You're going to graph right 1, 0, and right 10, up 1, and draw your logarithmic function. All right, what's your domain, class? Well, first of all, the asymptote on this is x equals 0. What is the domain?
0 infinite.
0 to the right forever. What's the range?
All real numbers infinite.
All real numbers. And this does not flatline, by the way. So this doesn't go flat. It's going up slowly, but it's going up forever. So it's going right forever and it's going up forever. Turn on. Y equals log base 4 of x. That is apparent. The reason why it's the most basic graph, there's no A, B, H, or K. It's just the most basic graph. We know that there's a vertical asymptote at x equals 0. And we want to pick 2 points to graph. So what x would you pick?
Would it be 1
Uh-huh.
and 4?
Here we go. So here's the first property. Log base 4 of 1 is what? Log base 4 of 1 is what?
What is 0?
Right. Okay, give me another nice x. You can pick any x you want, but give me a nice one.
4, because the
Right.
base is 4.
Right. So what's log base 4 of 4 to the 1?
1.
So you would graph right 1, 0, and you would graph right 4 up 1, and you would draw your logarithmic function along the vertical asymptote. All right, what's your domain?
0 infinite.
Open on 0 to the right forever, and what's the range?
All real numbers.
All real numbers. All right, so what about log base a half of x? Well, same thing, that is apparent, and it does have a vertical asymptote at x equals 0. And we want to pick 2 x's to graph. So what is the first x you would pick?
1.
What's log base a half of 1?
0.
Pick another nice x.
A half.
So what would log base a half of a half to the 1 be?
Just 1.
All right. So what we have here is we have right 1, 0, and we have right 1/2 up 1. And now we're seeing the inverse of exponential decay. So remember that exponential growth goes up and the inverse looks like that. This one, because the base is 1/2, its inverse is going to be exponential decay. So instead of trying to run the logarithm up, you're going to run the logarithm down. So what's your domain?
It'd be 0
So
to
it might be
infinity.
0, right? What's your range?
All real numbers.
All real numbers. Let's do another one with a base that's a fraction. Remember, we're just doing parents right now. And we're finding the parent points by using these two properties. Here's another parent. So once again, the logarithmic function has a vertical asymptote at x equals 0. And we want to pick 2 points. What x would you want?
1.
So what's log base a fifth of 1?
0.
0.
Pick another x.
1/5.
1.
What's log base a fifth of 1/5 to the 1 power?
1.
So we would go right 1, 0, and we would go right 1 out of 5 parts up 1. And of course, this is falling along the asymptote because its inverse is exponential decay. See, think about it. See how decay falls like that? See how it would reflect over the identity, and that would be the inverse? All right, what's your domain?
0, infinite.
And what's your range?
All real numbers. I have a question. Does the fact that the base is a fraction have to do anything with it decaying?
Yeah, because remember with exponential growth and decay, remember the growth were numbers greater than 1, but decay were the proper fractions between 0 and 1, like 1/5, 1/2, 3/4, 7/8, 11/12. All those proper fractions between 0 and 1 were exponential decay.
So still applying here, correct? Just okay, thank you.
So if the base is greater than 1, it's going to go up along the asymptote. If the base is between 0 and 1, it's going to fall along the asymptote. Okay, so what we just done, you guys, are the parents. And guess what? Guess what they're going to have you do in problem number 1. So if you're wondering, why are there only 8 problems? Because each problem has like 8 sections. So remember back in the day when school started in August, you had to find domain, range, and end behavior? Well, now they're going to ask for that. They're going to ask for vertical asymptote, horizontal asymptote, x-intercept, y-intercept, decreasing interval, increasing interval, negative interval, and positive interval. So they're going all the way back to the first week of school when you had to list all those characteristics. They're making you recall that now. All right. So I'm actually not going over that. So I'm going to assume you know how to do that. And if you don't, you're going to have to look it up and figure it out or ask somebody. I'm not going over that again. Okay, but what I am going to go over is this is actually what we just did was not even the first objective. So we're going to do the first objective now. Which is graphing logarithmic functions where e is greater than 1. So this is the base. So we're not doing any ones that fall. Going to all be going up along the asymptote. And they're going to ask you to do a whole bunch of stuff here. I'm not going to write it down. I'm just going to tell you. They're going to want you to state the transformation. They're going to want you to graph both the parent and the transform graph. They're going to want you to show the point transformation, and they're going to want you to state the domain and range using interval notation. So here we go. So the transform graph is -2 times log base 2 of x minus 1 minus 2. Now, the form of the equation is a times log base something, I'll just leave it like that, of bx minus h plus. Now, I just showed you the definition of the common log, but you realize this is log base z, whatever the base is. But there's your a, b, h, and k, as you probably already guessed. So how would you state the transformation here in the correct order? If that's the form, how do you state the transformation?
You would go right 1, vertical stretch by 2, reflection over the x-axis, and then down 2.
Reflect x and down 2. Okay, who's the parent? Who's the most basic graph? Log base what?
Log base 2.
Of x. All right, so who would your parent points be?
Would it be 1, 0 and 2, 1?
Right. It'd be log base 2 of 1 is 0, and log base 2 of 2 to the 1 is 1. And we have a vertical asymptote at x equals 0 with the parent. Now, let me ask you something. When we looked at exponential growth and decay, we had a horizontal asymptote that was affected by k. Who do you think affects the vertical asymptote?
H.
Yeah. All right, so let's put the points over here. 1, 0, right 2, up 1. And just do the transformation. So right 1 would be 2, right 1 would be 3. The y stay the same. Vertical stretch by 2, multiply the y by 2. Multiply the y by 2. Reflect x is a vertical movement, so we're going to negate y. Negate y. And finally, down 2 means subtract 2 from y. Subtract 2 from y. Okay, before I go on, did you guys get that? I did it kind of quick, but I want to make sure you agree with me. Right 2 down 2 and right 3 down 4.
Yeah, I got that too.
Okay, and so we want to write the new asymptote. They'll ask you to state it. What's the new asymptote?
Would it be x equals 1, positive 1?
If h is right 1, the asymptote's going to be shifted right 1. Right?
Yes.
By the way, in this form, you guys, the base, whatever the base is, let's just call it z, that has to be greater than 1. So it cannot be negative, it cannot be 0, and it cannot be 1, the base. It's got to be greater than 1. In fact, if you look in your book, once again, they're afraid to show the horizontal stretch of compression. So they're making the base of the log b, but you know that's not that's not the horizontal stretch of compression. The horizontal stretch of compression is in front of the x. Base of the logarithm. I'm calling it b for the base of the logarithm. All right, so we're going to graph both graphs. That's what they're requesting. So we'll graph the parent in black. So we have a vertical asymptote at x equals 0, and we're graphing right 1, 0, and right 2, up 1. So the domain of f would be 0 to infinity, and the range of f would be all real numbers. Let me check this again. Okay, guess what? They're not asking for the domain and range of the parent. So they're only asking for the domain and range of G. So with our transform graph, we have a vertical asymptote at x equals 1. You're going to graph the points right 2 down 2 and right 3 down 4. Now remember, this was reflected. So remember, your parent looks like this along the asymptote, but now he was reflected. So he's gonna be reflected and look like this, right? Yes, no?
Yes.
So he's going like this. And they want the domain and range of G. So what's the domain of G?
1 infinite.
Open on 1 to the right forever, and the range is negative infinity to infinity. So you just have to read the directions. They want you to graph both graphs, but they only want the domain and range of the transform function. And they might ask you for the asymptote. So they might ask you for both asymptotes, or they might just ask you for the transform function asymptote. Let's try another one. Actually, you know what? I'm going to put this on the board, and then I just want you guys to do it, and then we'll check it. So grab a piece of paper or in your notes and do this problem. Okay, so really all I want you to do, I want you to graph the parent and the transform function, but I only want to know the vertical asymptote of G and the domain and range of G. Okay? I'll give you a couple minutes to do that. Okay, can somebody read off your transformation really quick? I'm not gonna write it. What was the transformation?
I got left 2, vertical stretch by 2, up 4.
Right. All right. I'm also not gonna graph the parent. So I'm only gonna graph G. Who is the vertical asymptote for G?
X is equal to -2.
Okay, what points did you get at the end to graph? What were your final points to graph?
Final, I got -1, 4, and 8 and 6.
Okay, that's correct. All right, so we go left 1 up 4. And we go right 8 up 6. 1, 2, 3, 4, 5, 6, 7, 8. And there was no reflection. It was just left, vertical stretch and up. So there's no, it's still running, this graph is still running up along the asymptote. So what you do is you just run the graph along the asymptote. And what did you get for the domain and range of G?
Domain, I got 2 to infinite, and then range, all
2?
reference. -2.
And all real numbers. Okay, that's great. All right, any questions about anything I skipped on this?
So when something just says log with no base, it's just to assume that it's log base 10, correct?
It is base 10. It's there. We're not assuming anything. It's a common logarithm. So it is base 10.
Thank you.
So just like x is 1x, just like x is x to the first power, you see a logarithm like that, it's a base 10. Okay, let's do another one for you guys can do. It's g of x equals 1/2 times log base 2 of x plus 1 plus 2. So you guys go ahead and do this, and then we'll do it together kind of like we did this one and see if you can do it. Vertical asymptote is it? Okay, let's have somebody different state the transformation. What did you get for the transformation?
Oh, I got to the left 1, then a vertical compression by 1/2, and then up 2.
Yeah. All right. So did the asymptote move at all? Class?
Yeah, I
Yeah.
went to the left 1.
Okay. All right. And what did you guys end up with for your final points?
I got 0, 2 and -1/2, 5/2.
-1/2? Did you say one? What'd you say on that one?
Oh, sorry, -1/2, comma 5/2 were my final point.
Okay, can you check that again? Check that again, Pedro. Check it again for me, please.
Okay.
Anybody get anything different? The parent points were 1, 0, 2, 1, right? Okay, this is one of the final points. What did somebody get for the other final point?
1/2 and 3.
Okay, I'm not getting that. That doesn't mean I'm right.
I
Did
think I
anybody
found my
get?
mistake. Is it 1, comma 5/2?
Yes,
Okay.
1 and 5/2, which is 2.5. Okay, did everybody get that, or do you need me to do it?
I got that too.
The rest of you, are you okay? Can you do me
Yeah,
a
I got
favor?
that.
I'm gonna open up the chat, and can you just put a Y if you're okay? Hold on a minute, I gotta open it up. Here we go. I'm gonna open the chat up, and can you just put a Y if you're okay? Okay, we have 24 students. That's pretty good. That's pretty good. Okay, so here we go. So we have a vertical asymptote at x equals -1. She put an arrow on top and bottom. Then we're going 0 up 2, and this is right 1 up 2.5. So right 1 up 2.5. And once again, there was no reflection or anything. So this graph is going up along the asymptote. So your domain would be open on -1 to the right. Range is all real numbers. And remember what I said about that? The domain and range switch from exponential growth and decay. So if you remember all the growth and decay, the domains were -infinity to infinity. They just switch now. All right, well, guess what? That's the lesson. We're not going to do any word problems. We're not going to write, graph, or analyze anything. We're only doing problems 1 through 8. And I am going to include the practice AB. In this assignment, don't worry about average rate of change. So I think somewhere they're asking you to write average rate of change or something. Don't worry about average rate of change anywhere in this lesson. Okay? All right, so what I'd like to do, we have some time, it's 1:35. I want to go into the Math Wizard teams, and I want to specifically look at this graphing logarithmic functions. And I do want you to start with problem number 1, because that's the one that's asking about all that stuff that we learned in August, and you guys can help each other recall that information. Okay? I'll see you back here at 2:05, just to make sure that there's nothing major going on, majorly wrong. So
What lesson is this posted under?
it's not posted yet, because I've been having all these issues with my laptop. I haven't been able to work. And that's what people don't understand. It's like they want to keep my laptop for 4 days. Like, you can't keep my laptop for 4 days. I'm teaching. I don't know what other people are doing, but I have to have my laptop. So anyhow, it's not posted, but on page 754, that's lesson 15.1. Did you guys have any questions about 15.1? Are you guys doing okay? Okay. lesson 15.2, we're on page 770, and we're going to be doing problems 1 through 8. So it's 770 through 772, 1 through 8, and I have not posted it yet. Another reason why I haven't posted it, well, I wasn't even sure if I'd be able to teach today, so I wasn't even sure if I'd be able to teach this lesson. So yeah, it's not posted. I can't tell you when it's due yet. All right, I'm going to see in your teams. Make sure that you guys know exactly what you're doing with problem number 1. Okay? All right, I'll see you in your teams. All right, so basically, remember what I said in problem number, it's not problem number 2, not 1. Don't worry about the average rate of change. In problem number 2, they're asking you to give the intervals for positive and negative. Remember that positive means where the graph is above the x-axis, but you're stating it, the interval as the domain of it. Negative is where it's below the x-axis and you're stating the domain of it. Remember, all intervals like that are open. The other question about it increasing, it's increasing, all 3 graphs are increasing on the entire domain, which is 0 to infinity. So the graphs are not decreasing at all. All right. Did you guys want to ask me any questions about anything? Isn't a whole lot to clear up. So, okay. So once again, lesson 15.2 is not posted. I will post it when I can, but I'm just letting you know that it's 1 through 8, and I'll be assigning the practice AB and the online stuff also. All right. Listen, I hope you have a great day. Okay. Have a great day, and I'll see you what, Wednesday. See you Wednesday. Bye, guys.
Good rest of your day.
Thanks, guys. You too. Bye. Have a good day.